Hello. So this is video number 3 of section 6.2. Sorry, I'm usually recording these a few days ahead of the class, so I had to quickly reorient myself and remember that I'm in fact recording for chapter 6. So anyways, so far this section, we've defined what it means to be an orthogonal set. Then we looked at how we can sort of apply this idea of being an orthogonal vector and, orthogonality kind of representing, a 90-degree angle between vectors to sort of find this projection on, of y onto u, which, involved basically finding the vector that was scalar multiple of u, shortest distance to y. I want to return now to an idea of orthogonal sets, but I want to narrow our focus even more now when we look at orthogonal bases. So we say that a set of vectors is orthonormal if this set of vectors is orthogonal and, so again, restricting our focus now, a set of unit vectors. And remember, a unit vector is just a vector whose length is equal to 1, or the norm of this vector is equal to 1. And then on top of that, if W is a subspace spanned by this set of vectors, well then, since this set of vectors is orthogonal, it is a basis for W. But since it is also orthonormal, we say that it is an orthonormal basis for W. So I have on the board behind me 2 examples of orthonormal bases. I will label these vectors here now too. The first one is just the standard basis in R3. So this would be an orthonormal basis for R3. This is like always the best example of any basis because it's the easiest basis to work with and always kind of satisfies, as you can see, satisfies 2 properties we like to be satisfied in bases. So any pair of vectors is orthogonal. You can kind of see that without having to actually calculate the 3 different products. Because notice here, if we were to take the dot product of these 2 vectors, the 2 ones, right, so the only 2 non-zero terms we'd have to worry about don't even match up, and so we'd get 0 plus 0 plus 0, and we'd get the same trend for any pair of these 2 vectors you wanted to choose. Finally, the length of these vectors is 1, so I did the calculation here for E1, because remember, this is just the square root of the sums of the entries squared is the norm of a vector. And so as you can see here, you'd get the same calculation for E2 and E3, except maybe this 1 would appear in a different order somewhere in this sum. But thankfully, unlike matrix multiplication, we know that addition is in general commutative, so we don't have to worry too much about E2 and E3. So that one is very nice because it it's just an easy orthonormal basis. Not always that exciting, right, because there's not much to show. So let's look at one that maybe you could say is a little more exciting. So this is an orthonormal basis, and most orthonormal bases are going to look like this and not like this. So usually, eventually, as we'll see, we actually end up taking bases. So what we'll learn later this chapter called the Gram-Schmidt process is where we'll actually take a basis and in a sense transform it into an orthogonal or even an orthonormal basis. And so generally the process of transforming a basis into an orthonormal basis, you wind up with something that looks like this. Because basically what we're going to do is normalize each vector. So we're going to be dividing by its norm to turn this vector into a unit vector. And that's so going to look like this because we're going to be dividing by a lot of square roots. And sometimes the book is nice to us, and sometimes it'll like give us you might get like the squared entries that sum to 36. It's like, okay, I don't have to deal with square roots in the denominator, but we'll be dealing with a lot of square roots in denominators, unfortunately. So to see that this is orthonormal, again, I probably won't do all of these. We'll do the norm of U1. So this is equal to the square root of 3 over square root 11 squared plus 1 over square root 11 squared plus 1 over square root 11 squared. And so notice that when I square these, the denominators are all going to become just regular 11. And so as you can see, this is equal to the square root of 11 over 11, or equal to 1. And so if you want to check the other two to make sure that they are in fact also unit vectors, you can. And then maybe I'll do, just for the fun of it, maybe we'll verify that, let's see, I don't think I could do 6 times 66 very accurately, so maybe we'll verify that U1 and U2 are in fact orthogonal. So now we want to verify that U1 dot U2 is equal to 0. So this should be 3 times negative 1 over the square root of 6 times 11 plus 1 times 2 over the square root of 6 times 11. And actually, I guess really the denominator doesn't matter here because we just want to make this 0. So this is equal to negative 3 plus 2 plus 1 over the square root of 66. And sure enough, that's equal to 0. So you'd want to verify that all pairs, again, their dot product is equal to 0, and then U2 and U3 also have norm 1. And so this, along with this, would also be an orthonormal basis for R3. And again, you know it's in a basis because remember earlier this section, we did prove this theorem which says that if I've got a set of orthogonal vectors, remember that means we actually know that that set of vectors is linearly independent. And of course, we know that if we have 3 linearly independent vectors in R3, it's immediately a basis. So with all of that out of the way, let us get on to some facts that we actually can now learn about orthonormal bases and orthonormal sets of vectors. So it turns out that we like to study matrices with orthonormal columns. And so actually, I guess it's sort of self-explanatory. We say that a matrix U has orthonormal columns if the set of columns of the matrix, right? So if I look at all of the columns of the matrix as a set of vectors, right, that it forms an orthonormal set. And so we say that an m by m matrix U has orthonormal columns. And actually, maybe I'll define this a little more. So we'll say U is equal to U1 through UN. So there are the columns of U, has orthonormal columns. And so that is, this means that the set U1 through UN is orthonormal. If and only if U transpose times U is equal to the n by n identity matrix. So if U has orthonormal columns, remember that means that any two of these columns that are different, their dot product is equal to 0. And any two of these columns that are the same, that is U1 dot U1, is always equal to 1. Then U transpose times U is equal to the identity matrix. And so in a weird way, we kind of have this like non-square matrix, which almost kind of has an inverse in a way, right? Like, you know, these technically aren't inverses of each other, but like they kind of look like it in, you know, in a weird way. But so anyways, so your book does something like this, and I'm going to do something like this, except I don't even think you have to get as complex as your book to really see what's going on. We're just going to assume here for the proof that n is equal to 2. So that is that U is a matrix with 2 columns. And notice we don't really care how many rows U has as much as we do just looking at 2 columns of U. Your book does it with 3 columns, so if you want kind of another example of how this proof goes, I'd recommend looking at that on page 345. So this means we can express U transpose. We can actually define it by its rows, because remember the columns of U are the rows of U transpose. And so notice here, column 1 of U is equal to row 1 of U transpose. Column 2 of U is equal to row 2 of U transpose. And since vectors are just technically matrices with 1 column, this transpose notation makes sense, right? We basically just taken U1 and laid it out horizontally. So then we want to calculate U transpose times U, which is equal to U1 transpose, U2 transpose times U1, U2. And so we can actually now do the matrix multiplication dance here, right? So if you imagine doing this, you'd match up, you'd get a 2 by 2 matrix where we had U1 transpose times U1, U1 transpose times U2, U2 transpose times U1, and finally U2 transpose times U2. And so this is from matching up these imaginary rows and columns. Well, remember the sort of alternative way of defining the dot product, right? This is actually just the dot product. So this is actually just equal to U1 dot U1, U1 dot U2, U2 dot U1, and U2 dot U2. Right? Because if you imagine taking one vector as a row and matching it up with another vector, basically when we were doing matrix multiplication, back with the matrix multiplication dance, we're actually just secretly taking the dot product of rows and columns. And so that's all that's happening here with these 2 matrices. So U1 transpose times U1 is, again, secretly just the dot product of U1 and U1. But we know that these columns are orthonormal. Therefore, the dot product of U1 with itself is equal to 1, U1 with U2 is equal to 0, and U2 with itself is equal to 1. And so basically you get the same idea in any dimension. And you could show this, if you had any number of columns, where basically when you multiply out U transpose and U in this way, every time 2 non-same indexed columns and rows match up, you get a 0. And every time the same indexed column and rows match up, you get a 1. And that always happens the same matching up on the diagonal. So, very nice, right? We get this sort of cool thing that we can have this non-square matrix that, if it's orthonormal columns, all we need to do is multiply it by its transpose, and we get this nice, almost inverse looking like thing. So, matrices with orthonormal columns, and I apologize if I've repeated myself a few times now. Maybe not, though. I can't remember. We like matrices with orthonormal columns because, remember, all matrices end up representing linear transformations from Rn to Rm. And as we'll see here, with this theorem, matrices with orthonormal columns possess some really nice properties when we look at them as linear transformations. And so these types of things are very much desired when we are looking at matrices as linear transformations with applications to computer algorithms. So in a lot of applications of computer algorithms where you're dealing with linear transformations, you want to work with matrices with orthonormal columns. So why is that? Well, and actually, just to remind us, so remember that U represents a linear transformation from Rn to Rm, right, where every vector x in Rn gets descent to the vector U times x. All right, so keep this in mind as I start to list off all these properties, and then either before or after the proof, we can talk about what these properties mean in this context. So the first property is that the norm, or the length of U times x, is the same as the length of x. So right off the bat, notice as a linear transformation, U will always send x to a vector of the same length. On top of that, U times x dot U times y is always equal to the dot product of x and y. So it also preserves the value of dot products, which means, and this property follows directly from B, but it's important enough to state it on its own, that U also preserves orthogonality. That is, if two vectors x and y were orthogonal in Rn, then their images under this linear transformation defined by U are also orthogonal in Rm, which is also a very nice property that we want out of a linear transformation, right? We like these transformations which can preserve as many properties as possible. And so what we can see here is that a lot of properties we care about when studying vectors, orthogonality for one, length, are preserved when we use a linear transformation with orthonormal columns. So I believe you can actually use part B here to get both parts C and A, right? And so you can see part C actually just immediately follows from part B, right? That so notice here x dot y, if these were equal to 0, then of course ux times dot uy, there should be a dot here, is also equal to 0. So we actually only need to prove part B. So this is going to be one of those proofs where we kind of want to start out with one side of this equation, remember what we know about U, and try to kind of work our way to the other side. So what I'm going to do is start with this, and eventually I want to create a long string of equal signs which get me to this. So how do I start? Well, there's something about U that I'm not immediately using in this relationship. It's that U is orthonormal, right? That is that U times U transpose is equal to the identity matrix. So somewhere in here, I would like to get a transpose. Well, remember that the dot product, right, these are two vectors. The dot product is actually equal to the transpose of this matrix, or of this vector, excuse me, times this vector, right? So I've changed this from dot product notation to transpose notation, right? So you can think here, each of these vectors was vertical. I've just changed this to be a horizontal vector now, and now this is just well defined as matrix multiplication. But that is equal to, by the properties of transposes, I can distribute the transpose through and say that this is equal to x transpose U transpose times U y. But then I can just get rid of these parentheses here. U transpose U is equal to the identity matrix So that can just be thrown out of the equation. And then remember, x transpose y is the same thing as x dot product y. And that actually proves part B. And so notice part A follows from part B by just replacing this y with another x. And then, the square root part of the norm doesn't really matter here. And then part C follows because, of course, if this was equal to 0, then this is equal to 0, meaning these two vectors are still orthogonal. So, very nice properties we get when we look at matrices with orthonormal columns. So, I've got a few more things I want to do in this video. There are a few theory problems at the end of this section that I thought would be good practice. I also have one more thing I need to define, which is quite important. And if you ask me a little pedantic, well, I'll give you the definition. So in the case that a matrix with orthonormal columns is square, so if a square matrix U is, we'll say has orthonormal columns, then we call U an orthogonal matrix. So I don't love this definition because, the word orthogonal is being used in a different case, but remember, orthogonal matrix means square matrix with orthonormal columns. I'm not a huge fan, but that's what it is. And so in this case, this is a very cool matrix because, remember, now that U is square, it makes sense to talk about inverses. And so this is a square matrix whose transpose is its inverse. And so that's pretty cool, if you ask me. So there are 3 theory problems that I wanted to end this section with. I think I will do one of them, talk a little bit about it. The other 2 I'll leave as exercises. However, I will post the solutions. So the first one, actually, I think you've seen before, but we'll say, since we used this definition, we can apply it for this type of a problem. So if U is an orthogonal matrix, then the determinant of U is equal to plus or minus 1. And so with this statement, we want to decide if it's always true, sometimes true, or never true. So pause the video, think about it. All right, this statement is always true. Why is that? So if U is an orthogonal matrix, so as we just learned, this means that U transpose times U is equal to the identity matrix, right? So working through this, we now have this. We want to eventually get to the determinant of U. So it might make sense to take the determinant of both sides of this equation. But remember, we do know a few things, right? The determinant is multiplicative for 1. And the determinant of the identity matrix is equal to 1. So at this point, we actually know, well, the determinant of U transpose and U are equal, right? So I could actually replace this with, if I wanted to go a step further, the determinant of U squared is equal to 1. But notice I've got a number times itself that is equal to 1. That's only possible if this number is equal to plus or minus 1. So statement 1 is always true. how I would have gone about this had I not already known the answer, I guess. What I would have done with this type of a problem is I probably would have looked at the identity matrix, right, which is a matrix with orthonormal columns, to verify. I might have looked at one more matrix with orthonormal columns that was like very small, like a 2x2 matrix with orthonormal columns, and checked. And then at that point, if the 2x2 matrix I looked at was satisfied this, it's very unlikely you would have found like a random 2x2 matrix that satisfied this statement. And so at that point, I would have then tried to prove this. And again, proving this, you want to start out with what do you know and where do you want to get to. So that wraps up section 6.2. We will move on next week to tomorrow to section 6.3.